Good morning. Welcome to my new show. It's called Miss Snowman Does Your Homework. All right, so the first two problems on this page use the definition of velocity. Okay, so we're going to use the same formulas for both speed and velocity. But if that speed or velocity is average, it means we get to use this really easy formula. And these first two problems are that. So I can tell because this uses the words average velocity. And here we talk about the speed of sound is also constant. Okay, so both of these are constant average velocity problems. And it means we can use this really simple formula, which is listed on your notes, but also on the front of your reference tables. It's the first formula in the reference tables. And they're using this V bar. And if you come down here, you see that V bar means average velocity or speed. Okay, so V equals D over T. So I'm going to list my data. So it says the distance to travel, 2 meters. And the average time is an extremely accurate 34.45 seconds. And we only need two variables for known pieces of data for this formula because it only has three terms in it. All right, so V equals D over T. And then we're going to substitute in with units, 2 meters, all over 34.45 seconds. And if you do the math here, you get that velocity is 0.06 meters per second. Super duper slow. All right. Couple of things here. When you're doing this on a quiz or a test, you need to have a formula, substitution with units, and this is a way of checking to make sure your units match. And more on that later, and then the answer with units. If you drop units in intermediate calculations, that is fine. All right. Second problem. Hans stands at the rim of the Grand Canyon and he's yodeling down and the sound is coming back up. All right. So what do we know? We know the time is 5.2 seconds and the speed of sound in air, which is also on your reference tables, is 340 meters per second. And we are looking for this number here. How deep is the canyon? Okay, again, because this is a constant velocity problem, I can use the constant velocity formula. So I'm going to plug in with units. 340 meters per second equals D over 5.2 seconds. Okay. Then I can cross multiply. So 1 times D is D equals 348 times 5.2. As I said, you can drop units in intermediate calculations. Sometimes people like to keep units in because it's a way of, it checks nicely. If your answer comes out in the right unit, it means that you probably didn't make another big mistake. But in this case, yeah, it's totally fine to drop them here or keep them. It's up to you. They need to be when you first substitute in. And then on your answer. And so if I do the math here, I get that D is equal to 1768 meters. Now, that is the distance the sound traveled, and the sound went down and then back up. So to find the depth of the canyon, we actually have to take that number and split it in half. And so the actual final answer of the depth is about 884 meters. Okay. Now, those are for your constant / average velocity problems. What we have here is accelerated motion, and it is very, very dangerous to use this formula here for any kind of accelerated motion. And the reason is we have different ways of talking about velocity, right? We have average, initial, final, and change in velocity. These are not interchangeable. And that is a mistake, and the danger in this problem is that people will put one of these other velocities in for average and then they get it wrong. So for any kind of accelerated motion, I'm going to recommend that we use one of these formulas, which are also on the reference tables. Okay, so here we go. So Maria is walking to her hairdresser. And so in this, I'm going to follow the directions that we gave you on the kinematics video. So recommend making a data table. So a VI, VF, D, A, and T. I'm going to run out of room here, but oh well. Okay, so she's walking to the hairdresser at 1.3 meters per second, and then she glances at her watch and realizes she's going to be late, and she speeds up. If you wanted to draw a little picture of this, little velocity time graph, basically it's going to look something like this. And so the initial velocity is going to be right there, and then the final velocity is going to be right there. Okay, so the initial velocity is 1.3 meters per second. She quickens her pace at a rate of 0.09 meters per second squared. This is an acceleration, since acceleration is measured in meters per second squared. It's the A that equals that. This is getting entirely too, I don't quite have enough room here, so I'm going to just, I guess these are all the same problems, so I can put it right here. 0.09 meters per second squared. And again, I know this is an acceleration because of the unit, and also because they said the rate of her pace, she quickens her pace at a rate, so she means how fast she's getting faster. So that's acceleration. All right, and then what's her speed after? The time is 10 seconds. And we want to know her speed. This is the unknown. And we don't know anything about this one, the distance, but we don't care either because no one asked. All right, so we want a formula that has all of these things in it and nothing else. Okay, so that's, let's see, we got VF, VI, A, and T. That looks like this one right here, VF equals VI plus AT. So I'm going to write the formula down and substitute in. So I'm going to keep VF as it is. Please don't turn that into an X. It's too generic. There's too many variables to keep up with without turning things into X's. All right. Plus acceleration is 0.09 meters per second squared. And that's times 10 seconds. All right. So I'm going to do these first two. But basically, if I do the math here, I will get that VF equals 2.2 meters per second. Okay. Now, this one is got to do with, do you know how fast a meter per second is? All right. And I recommend that you jot down somewhere what the actual size of the different units that we use as we use them. So on this sheet here, which you can find under the linear motion module, I've jotted down that 1 meter per second is equivalent to roughly 2 miles an hour. All right. So if she's going at 2.2 meters per second, that is roughly 4.4 miles per hour. A brisk walk is 3 miles an hour. A sprint would be much higher than that, so she is jogging. Okay. 4, Stuart loses control of his brakes on his scooter and rolls down Buffalo Street at a steady acceleration. True story. All right, let's go ahead and fill in our data table, and I'll leave room this time and not do the crappy job like last time. VF, D, A, and T. So the acceleration is 3.6 meters per second squared. He starts from rest. This is one of these key words that's really important to turn into a piece of data. He rolls a distance of 300 meters, so that's this guy here. And we want to know how fast he's going at the bottom. They didn't give us time. We don't know time, so time we're going to leave alone. Now, as soon as we have 3 numbers, we can find a formula. But you have to realize some of the numbers are not going to be overtly stated. We call this hidden information. So I suggest circling or noting any words like rest. Okay, so I need to pick a formula that has these things in it and nothing else. And the formula I'm going to choose is this one. This one here is the convenient one to use when you don't have time. So VF squared equals VI squared plus 2AB. All right. VI is 0. This whole term drops out. So I'm going to write VF squared equals 2 times the acceleration, which is 3.6. And the distance traveled is 300 meters. And so you get that VF squared is equal to some big number. I'm going to grab my calculator. Okay, sorry. All right, so let's see. 2 times 3.6 times 300 is, nope, 2. 2,160. But we need to take the square root of that because we want VF, not VF squared. So I'm going to take the square root of both sides. And I'll get that VF equals 46.5 meters per second. I'm just going to check my math there. Yeah. And I can do this. All right. All right. And then finally, Miss Snowman, foolishly late for work, speeds down West Hill. Must be a better year. Let's put our data table out. VIVFDAT. She speeds down at a speed of 300. So again, if we were going to graph this, it would look kind of like this. She starts at 30 meters per second, and then she's decelerating, right? All right, and we want to know how far she's traveled. And we could find that with this area here if we wanted, but we're going to do it with formulas this time. All right, so the initial velocity is 30 meters per second. That's roughly 60 miles an hour. She comes around a corner and finds a school bus, and she decelerates at a rate of 5 meters per second squared. Now, since this is a deceleration, we need to add the negative in, okay? Because she's slowing down. And then the time is 3.4 seconds, and we're looking for the distance. So we have our 3 pieces of data. We have enough to find the answer. We just have to pick our formula. And so the formula we're going to pick here is my favorite, D equals VIT plus 1/2 AT squared. All right, let's plug in. So D equals 30 meters per second times the time, which is 3.4 seconds, plus 1/2 times negative 5 meters per second squared times 3.4 seconds. Don't forget to square it. All right, you're going to need to do this whole term first. So just a little bit of algebra here. All right, I'm going to square the 3.4 first, and then multiply it by 2.5. All right, and I get that the D equals, this term is going to be negative 228.9. And 30 times 3.4 is 102. And when I subtract those, I get 73 meters. I am done.